As you can see, there are no missing values. Let's create independent and dependent variable. Let's split the data. Now, let's fit the model. Let's keep the alpha at 1. Now, what we see here is the intercept value is 24. Let's see what is the mean square error. RNC is 4.74. Let's check the coefficient of the model and also check R2 score. .67 is the R2 score. Now, let's use the grid search. Here we are defining a grid. First, let's create a dict. That's a negative mean absolute error. Now, let's read the result. The score is minus 3.5 and the configuration. Fusion is alpha as plus 0.7. Let's fit this with alpha points and try to predict. We can also check the evolution matrix. Now we see that the RMSE is 4.731. Compared to earlier, it has reduced slightly, as it was 4.741. But let's check the R2 score. R2 score is 0.678. It does not change much, but yes, it's slightly increased. Let's check the coefficient of ridge regression. As you can see a lot of negatives, it has penalized. If you see the earlier ones, not much of a penalization as compared to the optimal alpha value. So this is how you read the data and fit the ridge regression. Lasso regression. Lasso regression is a form of regression that shrinks the coefficient towards zero. This is done in order to reduce the complexity of the data. While ridge regression forces the coefficient very close to zero, it never makes it exactly zero. Lasso, on the other hand, forces some of the coefficient estimates to be exactly equal to zero with the help of a large tuning parameter, lambda. So Lasso performs variable selection or feature selection. Like ridge regression, Lasso also helps to reduce the learning of more complex data and reduce overfitting of the model. It also decreases the variance of the model without an increase in bias. The fitting procedure involves a loss function, also known as residual sum of squares or RSS. Loss, RSS, is nothing but the difference between the actual and predicted value. Let's take an example. Y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus up to beta p xp, where y equals independent variable, beta equals regression coefficient value, x equals dependent variable. It's clear that this variation differs from ridge regression only in penalizing the high coefficients. Here we use the sum of the absolute value of weights instead of squaring the weights. Application. Lasso regression is applied in datasets where we need to shrink parameter estimates towards zero in order to fight two sources of overfitting. An interesting application of lasso regression comes from the healthcare sector. This regression is used to build a model to help distinguish normal epithelial or stromal tissue from cancer tissue. This helps surgeons to determine the spread of prostate cancer in the patient's body. Lasso regression is also used by insurers to determine if a customer should be given insurance by analyzing the lifestyle of the customer through social media profiles. It is evident that this form regression has many applications where variable selection or feature selection is required. Now let us look at the data preparation and implementation of this model in the next video. Data preparation, model building, and performance evaluation. Part C in this video, we'll see lasso regression and its benefit. Let's start by importing the libraries. We're using the hitters data set. In this data set, we have the different batsmen. What is their average score, salary, how many runs have they scored, etc. Let's check the info. Overall, we have 322 observations and 22 columns. As you can see, there is null values in salary. Now, let's replace that with a median. You can clearly see that the missing values have been replaced. Let's create a dummy variable. Apart from name, there are other objects or categorical variable aspect, like division and new league. Let's convert that into a dummy variable. Let's create x and y variables. Let's create the lasso model. Intercept value is 342. Let's also get the coefficient. As you know that in lasso regression, it will utilize the attribute. And you can see the last attribute. New league has been penalized to 0. Let's try to optimize that. Before that, check the attitudes, like RMSE and R2 score. RMSE is 345. Let's check the R score. It is 0.36. Let's try to optimize using cross-validation. Now let's check the best alpha value. "14 is the best alpha we got from cross-validation. Let's use this value and see if we can tune it. As you can see, our MSEs are more. It has increased by 1%. Let's see what the coefficient of the tuned model is. As compared with the normal lasso, you can see it has penalized the other group attributes, like league and RBI. This is how the lasso regression will penalize. And this is how we fit our model. Let's have a quick recap of the lesson. In this lesson, we learned that regression is a supervised learning technique that establishes a relationship between a dependent variable x and an independent variable y. It is used to predict continuous values like temperature, age, and salary. We also discussed the application of regression in the oil and gas industry and in predicting events. Further, we covered the different types of regression, how to build a linear regression model and its applications, some important assumptions in regression analysis, logistic regression and the two types of logistic regression, oversampling using SMOT and its applications, data preparation and implementation of the different regression models, nonlinear data. To overcome this, we use polynomial regression. Ridge regression is a form of regression that shrinks the coefficient towards zero to reduce the complexity of the data. Lasso regression also shrinks the coefficient towards zero. The difference between ridge and lasso regressions is that lasso hand forces coefficients to be exactly zero. Machine Learning Introduction. Megan insisted that the team spent some time analyzing and discussing the classifiers to be used in the next development cycle. She felt it was crucial that they chose the right classifier for the input data. This would ensure that they get the best results and reduce bias in the outcomes. Sheila decided to focus on the different types of classification algorithms and their application types. She will also learn how to select performance parameters. She will take a deeper look at the different types of classifiers, like naive Bayes, stochastic gradient descent, k-nearest neighbors, decision tree, random forest, Boruta explained, and support vector machine. What are classification algorithms? Classification is an activity that classifies things into subcategories. This is done by an automated process or a machine. Visualize a home security system, being able to differentiate between the home resident and an intruder. Consider a machine being able to differentiate between leafy, root, and cruciferous vegetables at a wholesale market. Stated another way, classification is the job of identifying to which of a set of categories, subpopulations, and new observation belongs on the basis of a training set of data containing prior observations and whose categories of membership are known. Classification algorithms are then used to classify or categorize data into a class or category. They are also known as classifiers that map input data into a specific category. Data on which classifiers operate can be both structured and unstructured. Common classification algorithms are naive Bayes, linear classifiers, logistic regression, decision tree classifier, k-nearest neighbors, stochastic gradient descent SGD, classifier random forests, to name a few. To determine the type of classification to be used, the nature of input data is first read, its nature determined, and then the classifier to be used is decided. As machine learning aims to replicate human behavior, classifiers are used to solve an array of problems ranging from detecting health problems, classifying nature of certain diseases like cancer, facial and speech recognition, and self-driving cars. Businesses can use machine learning algorithms to reduce bias and outcomes and improve quality of products while rapidly scaling the business. Before understanding how various classifiers work, the next video examines the types of classification. Types of classification. Classification algorithms can fall into the following types: binary classification, multi-class classification, multi-label classification, and imbalance classification. Let us look at each of these types in detail. Binary classification. Binary classification divides the instances into two classes based on the classification rule. Typically, one class will be known as the traditional state and the other the abnormal state. For example, an apple being juicy and fresh is the traditional state of a task, and a rotten apple is the abnormal state. The traditional state will be assigned the class label 0, and the class with the abnormal state gets assigned the class label 1. Some of the popular algorithms that can be used for binary classification are logistic regression, k-nearest, neighbors, decision trees, support vector machine, and naive Bayes. We shall discuss these classification algorithms in more detail in the upcoming videos. Multi-class classification. Multi-class classification classifies the instances into more than 2 classes. In this type of classification, the classification tasks can have only one label assigned to them. For example, a tree can be a banyan tree or a palm tree, but not both. Examples of this type of classification are classifying plants into different species and optical character recognition. Unlike binary classification, the multi-class classification doesn't have the notion of normal and abnormal outcomes. Instead, it classifies as belonging to one among all the range of known classes. Some of the popular algorithms that can be used for multi-class classification include k-nearest neighbors, decision trees, naive Bayes, random forest, and gradient boosting. Again, a detailed discussion of these algorithms will be done later in this lesson. Moving on, let us now see what multi-label classification is. Multi-label classification refers to those classification tasks that have 2 or more class labels. Multi-label classification requires specialized algorithms. The algorithms used for either binary or multi-class classification will not be suitable. The algorithms that are commonly used are multi-label decision trees, multi-label random forests, and multi-label gradient boosting. Imbalance classification. Imbalance classification involves unequal distribution of classes. Imbalance classification tasks are more of a binary classification tasks where the majority of the training data belong to the traditional class and a very less belong to the abnormal class. Specialized techniques, including random undersampling, Smoot oversampling, are used to overcome this. This was about classification types. In the next video, we shall explore how to select the performance parameters. Application types and selection of performance parameters. Once the type of classification is decided and classifiers are applied on input data, the resulting model output is available with a probability or a category. Certain metrics are used to determine the effectiveness of the model, or in other words, measure its performance. We choose features while applying classifiers to the data set under consideration. We use metrics to monitor and measure model performance on the validation set. It's a way of getting feedback on whether the approach is working or not. One way to evaluate the performance of a classifier is to look at the confusion matrix. The confusion matrix is an intuitive and a relatively simple metric that can be effectively used to assess the correctness and accuracy of a model. It is used for classification problems where the outputs are often of 2 or more sorts of classes. Terms to help understand the confusion matrix. The following terms are used to describe the elements of a confusion matrix. Let's consider the example of a patient being tested for COVID-19 virus. To help you understand the terms, the hospital takes a sample from the patient, runs a test, and a classifier determines whether the patient is COVID positive or not. True positive, or TP, when the case detected to be positive is classified correctly as being positive and predicted as positive of 1. In this case, the result from the test and the condition of the patient matched true negative, or TN, is when the case is detected to be negative for COVID-19. It's classified correctly as being negative and prediction is negative of 0. False positive, or FP, suppose the patient did not have COVID-19 and was only showing symptoms of seasonal flu. Yet the test result declared the patient COVID-19 positive. This outcome is a false positive. The case is actually negative, but was falsely classified as positive. False negative, or FN, consider that the patient did have COVID-19 and the test result declared the patient COVID-19 negative. This outcome is a false negative. The case is actually positive, but was falsely classified as negative. In an ideal scenario, the model correctly classifies and predicts 0 false positives and 0 false negatives. In reality, no model is 100% accurate most times. A confusion matrix can be used to evaluate the performance of a model using 4 key metrics: accuracy, precision, recall or sensitivity, specificity. Accuracy. Accuracy is the number of correct predictions made by the model divided by the total number of predictions made. This tells us how often the model made correct predictions with respect to the example of the COVID-19 test result. Precision. Precision of a model is determined by applying the formula. Precision equals true positive by true positive plus false positive, where the denominator is the total number of positives. Predicted precision is also equals true positive TP by total predicted positive. Precision is a good metric to use when the cost of a false positive is high. In the example above, the cost to the patient being falsely detected as being COVID-19 positive is high, resulting in medical treatment costs, and possible hospitalization recall or sensitivity recall equals true positive by true positive plus false negative, which also implies that recall equals true positive by total actual positive. Recall is a very useful metric when the cost of a false negative is high. In the example, if the patient actually has COVID-19 and the model predicts a false outcome, patient is reported negative on COVID-19, the cost to the patient is critical. Specificity. Specificity is a metric that points to how many cases that were actually COVID-19 negative were correctly reported as negative. Specificity equals true negative by true negative plus false positive. This gives an overview of what metrics are commonly used to determine the performance of a model. The next lesson starts with the first of the classification algorithms. Naive Bayes. Naive Bayes classifier is a machine learning model that segregates different objects on the basis of certain features of variables. Naive Bayes classifiers are based on the Bayes theorem. Such a classifier predicts the probable occurrence of an event based on a prior knowledge of other associated events. For example, the probability that the price of a house is high can be better assessed if we have prior knowledge of the surrounding neighborhood. Bayes' theorem works on the principle of contingent probability. This is a measure of the probability that something will happen given that something else has already occurred. The probability is measured using the equation where probability of A is the probability of hypothesis H being true. This is referred to as the prior probability. Probability of B is the probability of the evidence. Probability A of B is the probability of the evidence given that hypothesis is true. Probability B of A is the probability of the hypothesis, given that the evidence is true. The different types of naive Bayes algorithms are Gaussian naive Bayes, multinomial naive Bayes, and Bernoulli naive Bayes. Applications of naive Bayes. Naive Bayes has a large number of applications in modern society. Naive Bayes helps identify the right fit for a job by classifying the skills mentioned in the resume of candidates. It helps classify content available in the publishing field based on the availability of the information in different sources like the press, social media, and other sources. It classifies the relevant tags and research papers and helps researchers gain access to the right content. Naive Bayes is used to classify legal papers and identify legal documents in any field. In political speech classification, naive Bayes has been used to determine the mentality of political candidates by classifying the speeches they've delivered and their choice of words. It can even help determine if there are any words or sentences used related to racial abuse. In the world of advertisements, naive Bayes has been used to classify whether there are any degrading sentences or words related to colorism in ad dialogues. Recruitment specialists use naive Bayes-based classifiers to check for gender discrimination in hiring practices. Naive Bayes classifiers are simple classifiers based on contingent probability, where each feature is considered separately. We'll discuss how naive Bayes is applied in the next video. Applying naive Bayes classifier in this video, we'll see how to build naive Bayes algorithm. Let's start by importing the required libraries. We will use sklearn dataset. Let's create X and Y dataset. We've created 2 clusters. Now, let's plot the dataset. You can see there are 2 clusters in our dataset. Now, to this dataset, let's fit naive Bayes. First, let's import the library. Now that we have the model, let's create a few variables to predict. Now we have predicted. Let's try to plot again and update these new predictions in the plot. Let's keep an alpha at 0.1. You can see 2,000 new predictions have been plotted. Predictions are in a light color, and the actuals are in a dark color. Now, let's see the probability of some of the variables. Let's try to predict the probability x mu, and let's check the data for the first 8. For the first one, we have a probability of 0.89. For the other 8, it has given the probability of 1 and 0. So that's how we get the probability. Now, for building the naive Bayes, you import from sklearn naive Bayes version and fit into your test and train. Stochastic gradient descent. Let's learn about stochastic gradient descent, or SGD, in this video. This is a common ML algorithm and forms the basis of neural networks. Let's start with the word gradient, that is a slope or slant. Gradient descent means descending a slope to reach the lowest point on that surface. In the graph you see on your screen, the lowest point of the parabola occurs when x equals 1. With a gradient descent algorithm, we aim to find the value of x such that y is minimum. Y is the objective function that the algorithm works upon in order to descend to the lowest point. With this understanding, let us now reflect on this definition of gradient descent. An iterative algorithm that starts from a random point on a function and then travels down. Its slopes and steps until it reaches the lowest point of that function. The steps involved in a gradient descent algorithm are: compute the gradient of the function, pick a random initial value for the parameters. In our case, we would differentiate y with respect to x, plug in the parameter values, and update the function. Calculate the step size for each feature. Step size equals gradient multiplied by learning rate. Calculate the new parameters. New params equals old params minus step size. Repeat steps 3 to 5 till the gradient is almost 0. The learning rate is a flexible parameter that influences the algorithm convergence towards the minimum. Larger learning rates, larger steps down the slope, the minimum may get missed, so we typically use small learning rates. Researchers have found that this gradient descent algorithm becomes very slow on large data sets. A set of 10,000 data points and 10 features may take as much as 10 million computations to complete the algorithm. This is where stochastic comes to the rescue. Stochastic means random. SGD randomly picks one data point in the whole data set at each iteration. This helps to hugely reduce the number of computations. SGD offers the advantages of speed, efficiency, and ease of implementation. As one might expect, SGD comes with some disadvantages. Due to frequent updates, the steps taken towards the minimum may be very noisy. This in turn may lengthen the time taken to reach the minima. The frequent updates are also computationally expensive. Applications of stochastic gradient descent. Companies, while scaling up, have a hard time keeping a check on the quality. Machine learning helps to automate the process check. In such cases, SGD helps tackle low-performance issues in the model created. It also helps speed up convergence in huge data sets, so it's very helpful in real-world scenarios with large-scale data. SGD is used in financial modeling to reduce inaccuracies in predictions. We will discuss the applications of stochastic gradient descent in the next video. Applying stochastic gradient descent. In this video, we'll see how to build a stochastic gradient from scratch. We'll be using a breast cancer dataset. Let's start by importing the required libraries. Let's load the dataset. Let's split the data into test and train. To fit in stochastic gradient descent, let's create a class. Let's call it Custom Perceptron. Now, let's initiate. Now that we have initiated, let's also define the fit. We are fitting x and y, and then adding predicted value. We are multiplying with the learning rate into expected value minus predicted value into xi. In this case, we are multiplying with predicted value, then multiply by 1. Let's also define activation and define predict. So we are converting the output. If greater than 0, we'll say 1, otherwise 0. Let's also define score. If target is not equal to output, we will have an increment in misclassified data count. Let's run this and initiate the n iterations at 100. And the learning rate will be 0.01. Let's fit the model. Now let's check the score. Let's also print for the train. So you can see the test is 90% and the train is 92%. This is good. We could optimize this further. So this is how you do stochastic gradient descent from scratch. K-nearest neighbors. K-nearest neighbor KNN is one of the main machine learning algorithms that supports the supervised learning technique. The algorithm assumes a similarity between the new and available cases and puts the new case into the most similar category to the available ones. The KNN algorithm stores all the available data and classifies data points based on the similarity measures. KNN algorithms are used for regression and classification problems. The diagram below represents a before KNN and after KNN scenario. KNN is a non-parametric algorithm and doesn't make assumptions about the data. The KNN algorithm at its training phase stores the data set. When it gets new data, it classifies that data into a category that's most similar to the new data. How does KNN work? Here is a step-by-step working of KNN. Step 1. In the first step of KNN, we load the training with test data. Step 2. We choose the value of K. That is, the nearest data points. K can be any integer. Step 3. For every point within the test data, do the subsequent steps. 3.1. Calculate the space between test data and every row of coaching data with the help of a tactics, such as Euclidean, Manhattan, or Hamming distance. Euclidean is the most commonly used method to calculate the distance. 3.2 support the space value and sort them in ascending order. 3.3 next, choose the highest K row from the sorted array. 3.4. Finally assign a category to the test point supporting the most frequent class of those rows. Step 4 end. Advantages of KNN algorithm. It is simple to implement. It is robust even with noisy training data. It is simple and effective if the training data is large. Disadvantages of KNN algorithm. The worth of K must always be determined. This can become quite complex. Calculating the space between the info points for all training samples can be computationally expensive. Applications. KNN is applied in the manufacturing industry. It classifies manufactured goods based on size, grading, priority, location. Applying K-nearest neighbors. In this video, we'll see how to build a KNN classifier model. Let's start by importing the required library. Let's split the data. We're using social network ad data. As you can see, here is the data set. We have gender, age, estimated salary, and whether they have purchased it or not. Let's check the info. There are no null values. Let's check how many people have purchased. So 257 people have not purchased and 143 people have purchased. Let's create a dummy variable for gender. Let's drop the gender column since we have converted it to dummy variable. Let's create X value. Since the data is in a different range, let's standardize. Let's use preprocessor. We'll use a standard scaler. Now, let's transform the features. We have transformed the data. Let's create a data frame. Now the data is transformed. Let's split our data into test and train. Let's split into 80 to 20. Now, let's import neighbor. We'll just use one neighbor, and then we'll try to fit that. Let's predict and try to evaluate. Let's import classification matrix and confusion matrix. So this is confusion matrix where 2 is classified and 4 is misclassified for the non-purchase case. Let's check the classification report. Let's use print. We were able to predict 93% accuracy. For the purchase, we were able to have a precision of 86 and recall of 93. And the F1 score is 0.83. This is how you build a k-nearest neighbor classifier.